conservation basically leads to the fact that there is no net force before, during the process. So the momentum before the process and the momentum after the process is the same. So I'll be a little vague here, associated with the process. And that implies that momentum before equal to momentum after. So conceptually, that's what it is. However, when you are trying to digest it, that's like downhill.
Down. Yep.
When you are trying to digest it, it's actually more difficult than that. I'll tell you why. Momentum conservation law is actually another way of viewing Newton's third law. So Newton's third law told you that action and reaction, they occur in pairs, or forces occur in pairs. So, think about your whatever is in front of you. It's an object, and there are molecular forces acting between every molecule in that object. Each and every one of them are interacting, either tugging or really pushing each other apart. That's what they're doing. But the stuff in front of you, whatever it is, the table, your pencil or your iPad or whatever it is, it's not going anywhere. It's just stuck there. It's sitting quietly without complaining in front of you. Why? Because all these processes going on inside it, if you could really stick your head in and see, the net force goes away. If you sum up all the forces, it goes away. Okay? So momentum conservation is related to this very rich concept. But we can't study the consequences of momentum conservation in its full glory. And I'll tell you why. Because imagine all the atoms and molecules that make up your pencil, let's say. We really don't have the computational capability in the world to study that in all its detail. We don't. Macroscopic number of molecules cannot be studied. So while we know the end result, the detailed calculation is very difficult. So we have to make simplifications. We have to whittle it down to ideas that are more manageable, and we do our work. So momentum conservation is one such super simplified, super, whittled down concept that we learn. And in momentum conservation, what we are taking is we are just taking one or two objects instead of that 10 to the power 23 molecules that are in your pencil or whatever, just one or two objects, and we are saying that, okay, fine, so I have a block here, this is like one object, I have a block there, that's like another object, and they collide, let's say. So this is one super simple interaction, it's just a collision. It's not like forces at a distance like we have in gravity, or like you will see in one or two with charged particles. It's not like that. It's very simple. It's like two objects just colliding, very macroscopic. So all you are saying is that its momentum before collision is equal to its momentum after collision. So suppose this has a mass m1, this has a mass m2, and this has a velocity v1, and this has a velocity v2. So let's say somehow they collide. Now, if v2 is moving to the right faster than v1, they won't collide. v2 would run away. I mean, m2 would run away. So we don't want that. We want the collision to happen. So in other words, we make the numbers conspire in such a way that the collision happens. So therefore, you can write initially m1 v1 initial, whatever the initial velocity was, plus m2 v2 initial. Now, V2 may have been going to the left and M1 may have been going to the right, in which case you have to put in the correct sign for V2 initial, right? And then at the end of the day, post-collision, you're not describing the collision. That's when forces are there. And the net force goes away. So you're not describing the collision. But before collision, this is what's going on. After collision, you have M1 V1 final is equal to M2 V2 final. So you can't get simpler than this, right? There are only two particles. You don't even have 5 particles. Even 5 particles would be extremely hard to do, by the way. It would be beyond a PhD thesis. It will be that hard to do. All right? So stuff gets hairy very quickly. Anyway, so this is what it is. Now we have collisions of various kinds, and as I told you, primarily we talk about elastic collisions, and we talk about inelastic collisions. So elastic collisions are collisions in which not only is momentum conserved, so this is valid, but you also have energy conserved. Now in this case, as it turns out, you have very simple objects that don't really interact. You have 2 blocks, okay? Can't get simpler than that. They don't interact long distance, that is. So therefore the only energy that matters is the kinetic energy. You don't have potential energy. So therefore I can write energy conservation in the form of kinetic energy. So this is the kinetic energy of this guy before collision. This is the kinetic energy of the next guy before collision. Now observe, here you can't have a minus sign with respect to each other, because this is a positive quantity, Vi square, and V1I square, and V2I square will also be a positive quantity. So therefore the energies add up. And it turns out that this sum must actually be equal to M1 V1 final square, which is the kinetic energy of the first mass post-collision plus the kinetic energy of the second mass post-collision. So these are the conditions that define what we mean by elastic collisions. All right? So as you can see, elastic collisions are actually harder to deal with. Why? Because you have more conditions to deal with. And therefore we have really done 1 or 2 examples of elastic collision in class, and I will find a couple more of elastic collisions as problems, and I'll request Rahul to kind of go over them if he can. I'm sure he can do that for you. So that's what elastic collisions are. Now, most collisions, on the other hand, are inelastic for obvious reasons. When things collide, at the very least, you hear a thud. You can hear other interesting noises, but at the very least, there's some sound energy that's emitted. That sound energy is gone, right? The sound dissipates in air. So almost all collisions, unless you arrange for them in perfect vacuum, and there is almost no such thing as perfect vacuum on Earth, you will have collisions that are actually somewhat inelastic. So in inelastic collisions, momentum may be conserved, but energy is not conserved. That's the hallmark of an inelastic collision. So, for example, let's give a simple example. And this is an example I actually had you work through in one of the quizzes. You have a rifle, you have a bullet in it. So initially the rifle and the bullet are just sitting still, so momentum is 0, right? Velocities are 0. Then you fire the rifle. As you fire the rifle, the bullet shoots out. So now the bullet has a momentum. So if bullet has a positive momentum before was 0, then your gun's got to have a negative momentum, which means your gun's got to recoil. So the fact that the gun recoils when you fire a bullet is no big deal. That's exactly what should be happening. And there are countless examples I can pick up where similar things we experience. In fact, our brains are very aware of how to deal with momentum conservation, because otherwise we would be falling everywhere. Anyway, see how the energy conservation fails. What was the energy of the system with the bullet and the gun before you fired? Nothing was moving. 0, right? But once things start to move, because energies add up, there is absolutely no way in hell you're going to get you're going to get a zero when you add up the energies. Energies are going to be a big number because the bullet has the kinetic energy half mv squared. Your gun has a kinetic energy another half mv squared. The two add up. So energy conservation won't hold, right? If a bomb explodes, before the bomb exploded, there was no energy. Kinetic energy, that is. After the bomb exploded, everything is positive. So energy before and energy after are different. So therefore, the fact that you have energy conservation in a process, this is special. This usually doesn't happen. And energy conservation, while it gives you more handles to do the problem, it also makes your working on a problem more complicated. So inelastic collisions are really the more common collisions. And if you think about it, the most important inelastic collisions we did had to do with things getting stuck to each other. So for example, you have a block, and the block comes and there is a larger block here, and this block gets stuck to the larger block after collision, and they decide to move together. So in other words, they share a common velocity after the collision. That's an example of an inelastic collision because the masses got stuck. In fact, in this case, if you explicitly calculate kinetic energy before and after, before would be some non-zero value, but after would also be a non-zero value but a different value. And we have done problems like this. The case that you had raised about the ballistic pendulum is interesting because it's a little bit of a nuanced problem. So here you have a bullet. This is actually a technique, I'm told, that's used to study bullet types and so on and so forth in forensic investigations. So suppose you have a block of wood, all right, and just standing there. So there is nothing going on with this block of wood. Now this bullet, it's been fired now. It comes in and it obviously hits the block of wood and it ends up somewhere inside, let's say. So clearly, from my previous example, you can already figure out that this is going to be an inelastic collision because the two masses became stuck together. So that's not a big surprise. That energy is not conserved. But wait a minute, there's something interesting going on. So the momentum here, as the bullet's coming in, is simply m1 times, let's say, v bullet initial. This one didn't have anything going on. But after the collision, you have m1, which is, let's call it mb, the bullet mass, okay? So you have the bullet mass, and you have the mass of the wooden block, let's call it mw. The two have gotten stuck together, and jointly they have some velocity v that they acquire now. And you can calculate that velocity v if you know everything else. Because clearly, momentum conservation tells you that this momentum must be equal to that momentum. So you got a relation. Let's not worry about the detail of the algebra because I'm sure you can do the algebra yourself. At least you should be able to. But now that you have the collision happen, you have something which is quite interesting. What you have is you have this guy here, with a bullet in it, which was initially like this at t equal to 0. Let's start a stopwatch now. T equal to 0, it's like this. The collision has just happened. But post-collision, what happens is this thing would swing up. In fact, it's been arranged in such a way that it's going to swing up. So let me exaggerate the swing a little bit. And let's say it swings up to some level here. Maybe it's not exaggerated enough, whatever. And then it goes back again. So you have a video camera, just like Rand's, and you're shooting what's going on, and you can clearly record the maximum point to which it swings before it swings back down. So you know exactly how high up it's gone before it stopped. So the center of mass of this thing, let's say, was in this level before collision. But after collision, because this swings up at the highest possible point it reaches, let's say it has raised itself by this amount, let's call it h. Now we know very well for a long time now that if something rises by a height h, there is potential energy in it, and that potential energy is going to be mgh. So in this case, the potential energy at this point would be m bullet plus m wood times g times h. That will be the potential energy here. In fact, that will be the total energy, because the motion will stop at the highest point of the swing before it starts to go back down, right? So now what happens is that over here, all the energy was kinetic. It just started to move out. So therefore, what happens is 1/2 mb plus mw times, we got a velocity here, v squared. So this was the energy just after collision, and you see this part of the process, energy is actually conserved. So the energy before and after must be the same. So here you have a problem where you have momentum conservation, no energy conservation before during collision, because it was a completely inelastic collision. But post collision, something super interesting happens, because post collision there is nothing else that prevents energy loss anymore. So you can use energy conservation to do the calculation post collision. So this is really a very cool problem, a very standard problem too, but a very cool problem where multiple layers of physics are coming in, nothing very complicated, but at the same time, stuff that you need to think about a little bit. All right, so in addition to the discussion we had, why don't you guys do me a favor? Yeah.
Would you not need extra energy for moving side to side?
Once it's not going to move, well, so I'm just taking part of the dynamics when it just swings up. But beyond this point, motion will continue, right?
But like, to get the change, it would have to move, which would create kinetic energy.
Which would create, yeah, but at this point it will have to stop.
Yeah.
Because think about it, you have gone up and you're going to come down. But going up and before coming down, your velocity will have to turn, right? So for velocity to turn, velocity will have to go to a 0 point, right? Because if you take that to be positive, that will be minus. So there will be a 0 point. So it is precisely at that 0 point of velocity that you have the maximum amplitude of the swing. And that's what your h gives you. H is the rise associated with that maximum amplitude. Now, I can try to make your life a little harder by saying, instead of giving you all those details, I can perhaps give you just this angle. Well, okay, fine. So do some sine theta cos theta business and do whatever it is that you need to figure out. But conceptually, this is the problem. Okay? So a lot of times, now that you guys are coming towards the end of the semester, I'm beginning to throw in pieces to a problem that I avoided before, which may be a bit of trig, which may be a bit of geometry, just to see that if you are retaining and are able to work with the things that we have developed, but may not have been called upon at the quiz level or maybe at the initial problem level, but it's going to be called upon now. So even now I'm trying to raise your skills on things that you have done so far, just so that you don't fall apart if these things are being brought up. Somebody asked about torque problems. So in the torque part of the problem, we had, so torque is all about tendency, how to evaluate the tendency of rotation. So torque actually is a rather weird concept, because you don't have to take torque about an axis in general. So when we first learn about torque, I gave you the example of the door, for example. Here you have an axis, and it makes a lot of sense for us when we think about applying a force at a certain distance, and if the force is so far away, you can generate a larger torque with a smaller force. If R is smaller, you need to use a larger force to generate the same torque. So with respect to an axis, rotational tendencies of the door, for example, we can understand in terms of force, distance, and what have you. But there is something about torque that I didn't really tell you in big detail because it would have been a bit too much. I can take torque of an object about any point. I can take my torque about some point on the ceiling. I can just imagine some axis running through the ceiling. This is me, and I can take my perpendicular distance with respect to an axis running through the ceiling that I draw, and nobody can stop me from doing it. Okay? So in other words, there is nothing that binds me to one particular axis, which may be a sensible thing to do in terms of the axis itself, to calculate torque. I can calculate torque of an object about any axis anywhere. It doesn't even have to physically exist. So this is something important about torque. Why am I telling you this? I'm telling you this because look at this wheel. And this wheel is able to turn about some axis here in this case. Now, let us say that I have wrapped a string around, and let's say the string kind of hangs out here. Imagine a yo-yo, for example. Have any of you played with yo-yos? So many of you have played with a yo-yo? Welcome to the club. But these guys haven't played with yo-yos. How boring are they? To play with a yo-yo, you should be able to do all these nice tricks. Anyway, so in a yo-yo you'll have a hang. In fact, one of the kids from 101 class years ago actually gifted me a really nice yo-yo at the end of the class. And I have it, I can show it to you. It's a red colored yo-yo. It's a beautiful one. Love to play with it from time to time. So in this case, you see what happens is the yo-yo is all about turning. And if you have ever played with a yo-yo, you are really managing that goddamn torque. That's all there is to it. So what it is that you pull the string with some force F. Now think about it. You applied the force F here, but forces can be translated in parallel. So therefore the force is in this line. And just by looking at it, you can tell it's perpendicular to something. Well, what is it perpendicular to? This is the axis. So I can from this force, and so I can connect the force and this point by actually drawing just a perpendicular here, and that is good enough to give me the torque that will be generated by the force I apply. So this is R, and this is actually perpendicular distance. So I'll just to remind myself, I'll put in an R perpendicular. That sign is called a perpendicular. So therefore the torque I'll generate, which is denoted by tau, is simply going to be R perpendicular times the force. I don't need to worry about any sine theta and stuff like that because I've already taken the perpendicular distance. All right. So this is the reason why I'm saying perpendicular distance, because if you take the perpendicular distance, in effect what you are doing is you are doing R sine theta, because if you look at the formula for torque I gave you, torque is R times F times sine theta. But theta is the angle between R and F. But if you take R perpendicular, that sine theta is sine 90, which is 1. Think about it. Think about it. These are things that you need to think about yourself, such that you can be clear about what we are doing. This is not something that should trip you up, but it does. I know why it does. So anyway, we'll do more, but let me do something that I did last time, and I know that this is going to generally cause some nightmares for students. Remember that ladder problem we did? So in that ladder problem, we calculated everything needed for equilibrium, because you wouldn't want to climb on a ladder that's going to fall, right? And I took you through a bunch of arguments. I'm going to repeat that because I think those arguments are not so simple. So suppose this is where the center of mass of the ladder is, and therefore the ladder has a mass m, and therefore the force associated with it, mg, force of gravity, in this case the weight, will be acting smack in the middle. Let's give it a name. Let's call it A, B, C. And now you already know that this ladder is pressing against the walls and the floor, the wall and the floor. So this is the floor, this is the wall. So I told you that I don't know what the hell is going on here, nor do I know what the hell is going on here, because there are forces at play and I don't know what they are. But so in general, the force here is going to be in some direction like that, and the force here is going to be in some direction like this. because the ladder is kind of pressing at a weird angle, so you expect some force along this direction or this direction or something. I don't know. The good thing is I don't need to know. I don't need to know because I know whatever forces I have, I can break them down into horizontal and vertical pieces. So this ladder is going to have a tendency to slip leftward, which means that the friction force has got to be rightward. So this is my friction force, and this is going to be therefore a normal force. I can call it N, and likewise there's going to be a normal force here. I can call this one N. Let's call this N2, let's call this N1, and there'll be a friction force here as well. But let us assume that that friction force is very tiny, because we don't really need to have a lot of friction on the vertical wall. In fact, it can be an icy wall. We'll still be able to climb if the floor support is good. Okay? So these are the forces. So first you set up the force equation, and that's easy to see because you have a rightward force at friction on here, you have a leftward force here. The sum of these two forces must be 0. Otherwise you won't have force equilibrium. The vertical forces are also very simple because you only have one mg in this problem and you only have one n1 which is vertical. So therefore you can argue that n1 minus mg is going to be 0. So that's your vertical force. Now you can make this problem a little bit more complicated. Suppose you yourself are standing on the ladder, right? So this is the ladder's mg, and you are somewhere here, let's say, and this is your mg. So you need to know the distance here. Eventually you take the torque, but everything else will remain the same. Again, you'll have a friction force, you'll have a normal force, you'll have a normal force. That's what you get. So now the horizontal forces would be this friction force minus that normal force is 0, and the vertical forces would be these two downward forces. This upward force N1 minus mg minus m prime g is 0. So you can't go wrong setting up the force equation. It's the simplest thing you can do. The torque equation is not all that simple, because if you think about it, the torque equation, you have to take torque about some point. You choose the point. Sometimes I tell you which point to take torque about, but this is one of the first times I expect you to make the judgment call to set up the torque equation. So you already know that torque tau is perpendicular distance times the force. So if you take a point such that most perpendicular distances go away, you reduce the number of torque calculations that you need to do. So in this case you can see at this point there are two forces at this point, at point A. So naturally you can't have a torque due to friction because friction force will pass through point A. This is where the friction force acts. I mean, I have drawn it here. And likewise, this normal force also acts at this point. So therefore, the torques from N1 and F friction are going to be 0. So all I need to do, for example, in this problem, is take torque of mg with A. That's one torque I'll take. So let's go over this. So mg is smack to the middle. See the perpendicular distance of mg. This is where students get tripped up a lot. So this is A. The perpendicular distance is only that much. Okay? That's the perpendicular distance. You can take a look. Because the point is that this is the way the force acts. This is the line. So this is the perpendicular distance. The other, so the torque therefore would be a downward force. This is the point. This is the perpendicular distance. So torque will be like this. Therefore, the direction of the torque will be associated with clockwise rotation. So you can take this torque with a negative sign. It doesn't matter. The other one will take care of itself then. The other force that will not have a torque is this force here, which we call N2. Now you see, if I extrapolate n2, the perpendicular distance of n2 is here. I did that. This is the perpendicular distance. In other words, this length. So the perpendicular distance calculation, you really got to be careful. You screw that up, you have just shot yourself very badly on the foot. You won't get very far. But you see, these are the two torques. So if I'm to write it up, I would simply say, I'm assuming I know the lengths. So I have mg times AC over 2, right? Half of AC. So that's going to be a clockwise torque with a minus. Plus, this is going to be N2 times BC. And this is going to be a counterclockwise torque, which is positive, and therefore the torque equation is just that in this case. Yeah.
So if force of friction is parallel to
It is passing through A.
what?
Force of friction is passing through A.
Yeah. Oh, okay.
The perpendicular distance of force of friction with A is 0. And same with N1. Yeah.
How do you know whether it's going counterclockwise or clockwise?
What is that? Okay. So just imagine this is your axis. Your axis is through A. So if you now have a body in which you're applying the force this way, the body will tend to rotate, right? About that axis. And that is clockwise. But here, the force is that way. So it's going to be counterclockwise. Very simple. There's any other questions? So be very clear on this. Okay. So just to let you know, next Tuesday, yeah.
Is clockwise negative and counterclockwise?
Okay. It doesn't matter. You take one to be negative, you take the other to be positive. So because they are just relative to each other. So there is nothing hard and fast about which one you take as positive. I often take clockwise positive myself, but most books don't. So when I say that, I say it the way I do. But I like to take clockwise. Yeah. No, because N1 is at a different point. And when you are calculating torque, when you are taking forces, force equation, you just are interested in the directions of the forces no matter where they are. But when you are calculating torque, you are calculating that what the rotation tendency of that force will be with respect to the axis. So now where the force is makes a difference. So you cannot replace mg by N1 because it's an independent condition. The two conditions are not related. That's a very important point. Okay, we should go to the quiz, but before that, just so that you know, there is a short chapter we will do on Tuesday, and that chapter is going to be on elasticity theory and a little bit of simple harmonic motion. So take a look at your lecture notes that I'll post, as well as the OpenStax book, because the simple harmonic motion is another bear of a chapter. Okay? That's going to give you guys a lot of problems. All right, let's get going.